All right. Good afternoon, everybody, and thank you for being here. Welcome to our July 2026 installment of ENERCALC Office Hours. For those of you who have been with us at previous office hours, you guys know the drill. We're going to blast through some quick housekeeping items, and then we'll get straight into today's program. So before we get going, I want to start with a quick sound check. If you direct your attention to the bottom menu of the Zoom window in your browser or desktop app, you'll see that we have the chat tool there. We also have our reaction emoji capabilities in there. If you're able to hear me right now, just go ahead and throw a thumbs up, give us an applause, what have you, your reaction of choice. That's perfect. Thank you guys so much. And then we also want to go ahead and do a sound check and visual check for our primary speaker. So Chelsea is going to go ahead and share her screen here in a moment. And once again, if you can hear Chelsea's voice and see her screen, then go ahead and give us a reaction. Go ahead, Chelsea.
Hello, everybody.
Fantastic. Thank you guys for your help with that. So now that we have our tech checks out of the way, we are going to go ahead and disable the chat. We'll move on to some introductions and get going with today's program. So as you guys know, my name is Seth Roseworm. I'm a senior structural engineer and software developer here at ENERCALC. Our presenter for today's monthly ENERCALC office hours is Chelsea Darnell-Zhang. Chelsea's a product engineer here at ENERCALC, and she splits her time between providing technical training for ENERCALC customers, working with the ENERCALC engineering team on the specifications and technical behavior of our software, customer support to our users, helping maintain a presence for ENERCALC at national and regional events throughout the U.S. across the structural engineering industry. Before joining ENERCALC, Chelsea was an engineer at a structural firm in the San Francisco Bay Area. During that time, she worked on a wide range of projects, including high-end residential homes, elementary schools, public parks, seismic design retrofits, and so on. She's an active member of the SEOC SE Pathways program, which aims to advance structural engineering in California by improving recruitment and retention of underrepresented groups in the profession. So for anybody who's new here this month, we always want to let you guys know that Office Hours is here to provide direct lines of communication between you guys, our customer base, and the ENERCALC engineering team. And there's several avenues we use to do that, mainly through showcasing new features and giving you guys monthly updates about what's new and what's the latest, greatest in the software. We show optimized design workflows where we do module-specific deep dives and walkthroughs. And then we always take time to do Q&A live with the audience. So if there's ever a question that's too involved or it's going to require deep digging and research, that'll be a better fit in some cases for our support team so they can dig deep and investigate your concerns, look under the hood where necessary. So in some cases, we may refer you to the support team, but we try to always answer your questions live to the extent that we can. As a minor point of order, you will notice that everybody's microphones are muted just to make sure we don't get any echo or feedback while Chelsea's presenting today. And as I mentioned, we do have open Q&A at the end of every session, including today's session. So to submit a question for today's Q&A, just use the Q&A dialog in the lower dashboard of your Zoom window. If you experience audio problems at any point during the session today, you should be able to either refresh your browser or hop out and rejoin the session. And if you ever need to rewatch today's program or share it with someone who wasn't able to attend, all these recordings get posted to the Office Hours playlist on ENERCALC's YouTube channel, which you can also access from the Office Hours page on enercalc.com. With that, I'm going to go ahead and hand it over to Chelsea to get going on today's program.
All right, everybody. Thanks, Seth, for the introduction. Thanks, everybody, for being here. Welcome to another session of our program. As Seth said, I'm Chelsea, and I'm excited to be presenting to you guys all today. Today, we're going to cover a note on PDH credit for our office hour sessions. We'll talk about ENERCALC's latest build, including what's new in ENERCALC. We'll jump into our main topic, which today is the restrained retaining wall module in ENERCALC. And then we'll wrap up with a live Q&A. So as Seth mentioned, please feel free to drop your questions in the Q&A dialogue at any point during the presentation, and then we'll tackle those at the end. For our live attendees, we do offer a half-hour PDH credit. The certificate uses the name you joined Zoom with. So if you joined with an anonymous username or something that you don't want on your certificate, you can go ahead and change that now. Following the session, you'll get an email with a link to download this certificate. So starting off, we'd like to remind everyone to make sure that they're on the latest ENERCALC build. The latest build as of today is 2026-0701. This was released just last week. ENERCALC releases monthly updates, and many of the support questions that we get, things like missing features or mismatches between hand calcs and program output, this stuff often comes down to running an outdated build. So please just take a moment to check your build and update it if needed to make sure that you're running the latest and greatest. If you could all just take a moment, pop open your software. You can check the build at the top of the program. If you're on an outdated build, you can easily download the latest build by selecting the update button in the upper ribbon. Clicking the update button opens the window shown on the left, where you can check for updates, launch the For Our Users page to download the latest build, subscribe to new build update emails, and these emails include release notes, which highlight the newly added features, bug fixes, and other important updates. And then in this window, you can also choose whether you'd like to be notified at program startup if there is an update available. So you can use the checkbox right here to do that. Now, if you've not been on the latest build, or maybe you just haven't really had time to poke around in ENERCALC recently, we wanted to highlight some newer features and functions that we hope that you can take advantage of on your projects. The first update I'm really excited to share. It is the reference loads and the project load group builder. The wood, steel, and concrete beam modules can now reference predefined load groups from the project load group builder directly in calculations. And then changes that are made in the project load group builder automatically populate every calculation that references these loads. And there's also a status badge monitoring system, which notifies the user when reference calculations need to be updated. The project load group builder can be found under the General tab in your project manager. And when you open the project load group builder, you'll find yourself here on this page. And here you can pull from ENERCALC supplied or your own user-defined load items to build these load groups and to create these weight takeoffs. You can create area, line, and point load groups. And once you have these load groups created, you can start referencing them in your calculations. Currently, reference loads are supported, as I said, in the wood, steel, and concrete beam modules. So if you pop open up one of those modules right now in the latest build and you navigate over to the Span Loads tab, you're going to find a new Reference Loads tab. Here you can select a load type and then choose the reference load that you want to use from the list of reference loads that you built. Calculations that have reference loads are going to include a status badge in the project manager. And when changes are made to the reference loads in the project load group builder, the status badge will change, letting you know that the calculation needs a recalc. Similar to linked loads, you can recalc these calculations in bulk using the recalculate button up at the top. And this is a really exciting update. This allows users to create typical load groups that can be referenced across the calculations in their project, and then bulk update that information if things change, like you have different floor weights or you need to adjust your live loads or something like that. So I'm really excited for users to check it out, and please let us know if you have any feedback on it. We're excited to hear how you're using this new feature. Another exciting update that was released in the last build is adjustable load graphics in some of our beam modules. The steel beam, wood beam, and concrete beam modules now allow load graphics and labels to be adjusted in the 2D diagram. Users can use the toggle in the lower left-hand corner to adjust graphics up and down, clarifying the view and maximizing legibility. Last month, we shared that access to Jack was available in ENERCALC, and this month, we are excited to share another update. The Ask Jack button on the main toolbar now opens a dedicated window, providing direct access to Jack, the ENERCALC AI support chatbot, without requiring a web browser or navigating to enercalc.ai. Jack is trained on ENERCALC documentation and product data, so he's a great resource for quick answers anytime you need them. We've made some recent updates to the building code information window, including new tabs to keep things better organized and more intuitive. All governing codes and material design standards can now be individually selected, so you can mix and match codes and standards to meet your jurisdiction's requirements. There's also a convenient sync button to bring all standards back in line with the selected IBC edition. Another update, load linking, is available in the steel beam, wood beam, steel column, wood column, and general foundation modules. Load linking gives users the ability to automatically link reactions from one calc to another, and the ability to change something in one member and have the effects of that change trickle down to all the supporting members. If you have not tried load linking yet and you would like to learn more, we do have a YouTube playlist with short step-by-step videos that can help you get started. And we recently uploaded a newer video that has a full practical example transferring reactions from beams to columns, and this covers both wood and steel members. And then the last update I want to share is ENERCALC for Revit has seen some new features recently. ENERCALC for Revit now includes the wood column module, along with support for engineered wood sections like LVL, PSL, and glulam members. Last month, Seth presented on EFR for wood buildings. And if you missed that session, I definitely encourage you to check it out. We have the recording on our office hours page on our website, and it would be a great way for you to see those new features in action. And now, moving on to our main event, the true focus of our session today is the design of retaining walls using the Restrained retaining wall module in ENERCALC. We're going to be covering the module's capabilities and limitations by walking through an example together. So I want to start off with a quick overview of the capabilities and features of this module. The best use of the module is for the analysis and design of retaining walls with a lateral restraint that is at or near the top of the wall. The module supports a variety of applied loads, including toe and heel surcharges, axial loads on stems, adjacent footing loads, lateral loads on stems, and wind and seismic forces as well. The module supports both pinned and fixed stem-based conditions, and the option to specify whether a slab is present at the top of the footing to resist sliding. The module will check soil bearing pressure, sliding stability, and masonry stems when ASD is selected for service level demands. And it will check concrete footings, concrete stems, and masonry stems when SD is selected for strength level demands. I also like to note that the module does have some limitations. So the Restrained module does not allow a sloped backfill. The retained soil must be level. The module does not provide a water table input, so saturated soil effects are not considered. The module assumes tension at the top of the heel. So in cases where you have significantly high axial loads with some eccentricity that might cause tension on the bottom face of the heel, it might be more appropriate to use ENERCALC's wall footing module instead. The module assumes a continuous support along the top of the wall. So if the connection to the top restraint only occurs at discrete points for your condition, then you might need to check the wall's ability to span between those points by doing some supplemental calculations outside of the program. And then lastly, the module does not automatically evaluate multiple load combinations. This is a limitation that we covered before in the cantilevered retaining wall office hours. And if you didn't attend that session, do not worry. We will be revisiting this limitation in more detail when we jump into the load factors tab. For today's example, we're going to say that we have been asked to design a concrete stem restrained retaining wall. The wall is going to be retaining 6 feet of soil, and the total wall height is going to be 10 feet. The lateral restraint will be at the top of the wall. We do not have a slab present to resist sliding forces, so sliding is going to be resisted with passive pressure and friction forces. The stem base will be fixed to the footing, and our design will be based on IBC 2024 and ACI 31819. And I'll be mentioning some differences between ACI 31814, 19, and 25 as they come up. Continuing on for our example, we have some additional applied loads. So we have 100 PSF heel surcharge, 100 150 PLF axial dead load at the face of the wall, and 15 PSF wind load on the portion of stem that extends above our retained soil. And then let's say our geotech has provided us the soil values that are shown here. So we can jump into our ENERCALC program now, and we can start a new retaining wall calculation by clicking Add, navigating to the Earth Retention tab, and selecting the Restrained retaining wall module. We're going to start with our inputs in the General tab, and then we'll work our way through the inputs, moving left to right to set up our calculation. Here on our General tab, we can give the calculation a unique name, and then we can start filling out the rest of our inputs. First, we'll define 4 key heights. This is going to be the retained height, the wall height above the retained soil, the height of soil over the toe, and then the location of our lateral restraint, which should be at or near the top of the wall. A couple of things to consider here. This module assumes, again, that the restraint is continuous along the top of the wall. Additionally, it is the engineer's responsibility to confirm that the actual restraint is stiff enough. So this assumption matters because the whole design approach for a restrained wall depends on the top stem being laterally restrained and unable to deflect. So since the top of the wall cannot move, soil pressure can approach the at-rest condition rather than the active condition that you would assume for a freestanding cantilevered wall. So the engineer has to determine whether that top restraint is truly adequate to prevent any lateral movement. A wood diaphragm, for example, might be too flexible to provide the stiffness needed for at-rest conditions to actually develop. So that's something for you to consider when you're choosing to use this module. Next, we'll define our soil values, which typically come from the project's geotechnical engineer. This module requires the user to enter the at-rest lateral soil pressure in pounds per cubic foot. Moving on to the loads tab, this is where we will enter any additional loads to be considered in the wall design. We can specify surcharges, axial loads, adjacent footing loads, lateral loads, wind loads, and seismic loads. For surcharge loads, we can apply live load surcharges to either the toe, the heel, or both sides of the wall. For strength checks, surcharges are going to use the live load factor that you've defined in the load factors tab. And then for service checks, a factor of 1.0 will be applied. We also have the option to specify whether these surcharges are going to be considered in our sliding and overturning calculations. We can confirm whether these surcharge loads are being used by toggling these checkboxes on and off, and then checking the moment summary results under the stability tab. While overturning is resisted by the lateral support at the top of the wall, overturning and resisting moments are still calculated in this module because they're used for our soil bearing pressure checks. For our example, we have a 100 PSF heel surcharge applied, and I have selected to consider the heel surcharge for our sliding and overturning. Next up, we can specify uniformly distributed axial, dead, and live loads that are applied to the top of the stem. This load type allows you to specify eccentricity measured from the center line of the top stem section. Positive eccentricity shifts the load towards the toe, and then negative eccentricity shifts the load towards the heel. And as I mentioned earlier in the limitations section, this module assumes tension at the top of the heel, which is why you'll see the heel reinforcement placed at the top of the footing in the construction view. So users should be cautious when they have high axial loads with eccentricities that are causing a reversal of bending and pushing tension down into the bottom face instead. When applying axial loads, another thing to keep in mind is that they're treated as uniform over the 12-inch design strip, and they're not going to be reduced along the wall height. If you're modeling a point load, like a beam or a girder reaction at the top of the wall, you might want to consider reducing the input to reflect how the load spreads downward along the wall. We covered this same limitation in the cantilevered retaining wall office hour session. And if you missed it, or if you need a refresher, we'll take a look at an example together. So let's say I have a 15 kip point load applied to a 2-foot wide bearing area at the top of my wall. In this case, I might consider reducing the axial load input to account for how the load spreads as it moves down the wall. So this is typically taken as a 2-to-1 slope. This is just kind of a rule of thumb. The spreading effect can reduce the compressive stress at the base of the stem. So since the stem design is based on forces at the base, a user might choose to enter an axial force of 1.25 KLF, which would be the 15 kip point load spread over an effective width of 12 feet. And then you may perform a separate hand calculation to check the local effect of the 15 kip point load at the top of the wall. If I choose to reduce the axial input, I'll also want to consider how many stem sections I'm evaluating. Compressive stresses would vary along the height, and since the restrained retaining wall analyzes the stem at 3 heights, it might be necessary to copy the model to test different axial inputs at each height. So this example is simply meant to illustrate how an engineer might apply these loads and evaluate the wall based on specific conditions. It's not a hard rule or a recommendation. Whether to reduce axial loads is going to be entirely up to the engineer's judgment. Moving on, users can also specify adjacent footing loads. Users have the option of placing a continuous line or square footing adjacent and parallel to the back of the wall. A Boussinesq analysis is used to calculate the vertical and lateral pressures acting on the stem and footing. And adjacent footing loads are factored by the live load factor for strength design. When the line load footing type is selected, the user should enter the continuous load per foot parallel to the wall, along with the footing width and the other dimensional information required for ENERCALC to perform the Boussinesq analysis. If the adjacent footing is another retaining wall at a higher elevation, the Boussinesq analysis is going to account for the vertical load that wall's footing is applying to the soil, but it will not account for the additional lateral sliding forces, and the design should include the additional lateral sliding forces from that adjacent retaining wall. So a user might choose to apply this lateral load as an applied lateral load on the stem in the section below, but that's up to the engineer's judgment and discretion. It is beyond the scope of the module. When the square footing type is selected, the user should enter the total load divided by the footing dimension that runs parallel to the wall. So if you have a 2,000-pound load on a 4-foot square footing, you would enter 500 pounds per foot, so the 2,000 pounds divided by 4 feet, into the magnitude box. And then the user will enter the other information in the section that ENERCALC needs to perform the analysis. For our example today, we don't have any adjacent footing loads, so we'll move on to our lateral load inputs. For lateral load inputs, we can apply dead, live, earth, wind, or seismic lateral loads to the stem. Dead, live, and earth loads should be entered as unfactored service level loads. For seismic and wind loads, you have the option to specify if that load is strength or service level. You can specify where the load occurs along the stem to model a uniform load over a certain height. This input can also be used to simulate a lateral point load. Like axial loads, these lateral loads are treated as uniform over the 12-inch design strip and are not reduced along the wall height. So like we discussed in the axial load section, a user might want to consider reducing the lateral point load input to account for how the load spreads as it moves down the wall. But again, this is up to the engineer's judgment. ENERCALC also provides a quick and easy way to apply wind loads on the stem above the retained height using the wind on stem above soil input. You simply enter the wind load magnitude and then you choose whether that is strength or service level. For our example, we're going to apply a 15 psf wind load to the stem above the soil. We can also choose to apply seismic lateral pressure by entering a KH factor in the seismic tab. Keep in mind that wind and seismic loads do not need to be considered at the same time. So for our example, we have wind loads applied and we're not going to be including any additional seismic load in this calc. Moving on to the stem tab, this is where we're going to define the stem material, fixity, and reinforcement. This tab's content changes depending on which material that you select. Stem sections can be concrete or masonry, but unlike the cantilevered module, the retained module requires one material for the entire stem with a consistent thickness for the entire stem. For both masonry and concrete wall types, the user can specify whether the stem base is fixed to the footing. If this box is left unchecked, the stem base will be considered pinned. and intermediate degrees of fixity are not supported. The program considers 3 stem design heights, so the base of the stem, the location of maximum positive moment, and the lateral support location. Moments are checked at all 3 locations, and then shears are checked at the base and lateral support. The user can choose to position the rebar at either the center or edge of the wall. If center is chosen, the rebar distance D will be half the actual wall thickness. And then if edge is chosen, the rebar location is going to vary along the stem height so that the rebar is located on the tension face of the wall. Now, I want to take a minute to talk about concrete stem design. For concrete, ENERCALC currently supports ACI 318, 14, 19, and 25. And you'll notice a few differences depending on which material design standard you select. One difference that is very noticeable is the difference in shear capacity. ACI 318.25, section 13.3.7.1C, always a mouthful. This allows a simplified shear equation for basement walls as an alternative to the one-way shear provisions that are in section 22.551. So if you select ACI 318.25 as your design standard, you'll see a checkbox on the STEM tab that lets you toggle whether to use that simplified equation. And this is the same equation that's used for concrete stem one-way shear under ACI 318.14. If you don't use the simplified equation, the program is going to default to equation C from table 25 or 22.551, and that is going to be the same equation that's used for concrete stem one-way shear under ACI 318.19. Another difference is in the hooked embedment modifiers. Toggling between material design standards will show different modifiers to match the respective hooked bar development length equations in ACI 318 chapter 25. When a masonry stem section is chosen, the user can specify if the design method should be allowable stress design or strength design. The user can also specify the CMU block type and a block weight modifier as needed to achieve the appropriate wall weight. The user can also specify whether the block is solid grouted. For our example, we have a concrete stem designed for ACI 318.19, and I've chosen to place the rebar at the center of the stem. Moving on to our footing tab, here users can specify the footing material properties, rebar cover, and minimum reinforcement ratios. Users can enter their toe width, heel width, footing thickness in this section. There's also a convenient quick access button that lets you instantly center the stem on the footing. Users also have the option to neglect the upward soil pressure, which typically results in a greater heel moment. So this can be helpful if you're trying to hand verify your heel moment, but upward pressure at the heel is typically considered in final design. The user can then specify toe and heel reinforcement, with both sections offering a list of acceptable rebar sizes and spacing. Clicking on the footing rebar details button opens up this pop-up window for some more in-depth information on your minimum and maximum reinforcement ratios that you can use for reference. If you have a key specified, you'll also see some key rebar data here. Below the toe and heel reinforcement inputs, there's a reference list of acceptable horizontal reinforcement sizes and spacing. So this makes it easy for you to review some options for your detailing. The next tab allows you to specify whether a slab is present to resist sliding forces and whether a key will be provided. If a slab is not present to resist sliding forces, you'll be able to specify the sliding resistance method, input details about the sliding resisting forces that need to be considered, and you'll also find the summary for the sliding forces below. If a slab is present to resist all sliding forces, you'll see the sliding resisting force inputs will be hidden. And when a slab is present, it's assumed to resist all lateral forces at the base of the wall. So the lateral force at the base of the stem is provided so the user can check the slab and slab connection for adequacy to resist that force. And something to note here, the slab is assumed to sit at the top of footing, and that position is not, you are not able to adjust that. For today's example, we do not have a key and we do not have a slab present to resist sliding forces. So we can move on to the sliding resistance section. Here you can choose whether sliding resistance is going to be calculated using friction and passive pressure or cohesion and passive pressure. You'll then enter the depth of passive pressure to neglect along with the friction factor or cohesion value and the percentage of passive and friction resistance to be used. These inputs are typically going to be provided by your geotechnical engineer. Now, let's talk about load factors. If you've watched the cantilevered retaining wall office hour session, this part might look a little familiar. Unlike most other ENERCALC modules, the cantilevered and restrained retaining wall modules don't let you directly select load combinations. Instead, you enter load factors into this tab, and then the program uses those factors to build the factored load combinations. So let's start with discussing strength design checks. The user is going to input load factors into this tab, and ENERCALC is going to use these load factors to create one factored load combination for our strength design checks. The strength design checks are going to include checks for the concrete stem, concrete footing, and then masonry design when SD or strength design is selected. Since wind and seismic don't need to be applied concurrently, users might want to run separate calculations to evaluate wind and seismic conditions. If you want to evaluate multiple strength design load combinations, so, one with wind, another with seismic, the recommended workflow is to first finalize all your inputs, and then you can make a copy of your retaining wall calculation, and you can run several versions. So you can do different load combinations, different loads applied, and then you'll be able to compare results and determine what is the governing case. Now let's look at our surface level checks. So this is going to include your soil bearing pressure, sliding, overturning, and masonry stem design when ASD is selected. For these service level checks, ENERCALC runs one combination where all applied loads are at the service level. So any strength level seismic loads are going to be converted down to service level with a factor of 0.7. Strength level wind loads are going to be converted to a service level with a factor of 0.6. And then all of your other load factors are set to 0. So that results in this combination here. Once again, if you need to consider both wind and seismic loading, or if you want to vary things like your live loads, it's best to create a copy of your calculation, and then from there you can adjust your load inputs and or load factors so you can run separate checks. Jumping back to our example today, these are the load factors that I've applied in this tab over on the left. And then over on the right, we can see the combinations that ENERCALC is going to run based on this input. Now that we have all of our inputs finalized, we can take a look at our outputs. Here we see our results summary tab, giving us an overview of our sliding factors of safety, bearing pressure, footing design, and stem design values. Here we see a note reminding us that overturning is resisted by the restraint at the top. And if there's no slab present, like in our example, we're going to see a sliding factor of safety in this section. Next, we can review our soil bearing pressures, confirming that our bearing pressure at the toe and heel are less than our allowable bearing pressure. I want to take a minute to look at what goes into the soil bearing pressure calculation together. So your eccentricity is going to be determined using the resisting moment, overturning moment, and total vertical load. And these moments and load are going to be all at service level. And then the eccentricity and service level total vertical load are used to determine the soil bearing pressure distribution. The bearing pressure distribution can be either trapezoidal or triangular, depending on where the resultant load falls within the kern or the middle third of the footing. When your eccentricity is less than or equal to your footing width divided by 6, the bearing pressure distribution will be trapezoidal, and the toe and heel soil pressures will be determined using these equations shown here. And then when eccentricity is greater than the footing width divided by 6, your bearing pressure distribution is going to be triangular. and your toe and heel soil pressures will be determined using these equations shown here. Moving on, we can review our footing bending and one-way shear checks. Similar to what we saw in our concrete stem tab, we are going to notice a difference in the one-way shear capacities in this tab depending on which material design standard we selected. ACI 318.14 and 318.25 are going to use the 2 times lambda equation. And then ACI 318.19 will use equation C from table 22.5.5.1, assuming no transverse reinforcement in the footing. And lastly, we can review our concrete stem results. Once we've reviewed the information in the summary tab, we can then click through the subsequent tabs to view some more detailed results. In the stem design values subtabs, we can review the rebar lap and embedment length table and the concrete rebar area details table. In the stability tab, we can review our sliding forces for our sliding checks and our resisting forces for our soil bearing pressure checks. In this module, overturning is not a failure mechanism that we check directly since the restraint is at the top of the wall and that resists our overturning forces. But as I've mentioned, overturning and resisting moments are going to still be calculated behind the scenes because that's what's used to determine our soil bearing pressure. One thing to note here is the overturning and resisting moments, and even the outputs that are reported in this tab, are going to vary depending on your stem fixity and then whether or not a slab is present to resist sliding forces. We're going to take a minute to walk through the 4 possible permutations of these and how these affect our sliding and soil bearing pressure calculations, because this is a common question that we get from our users. So the 4 possible permutations are going to be stem pinned with no slab, stem pinned with slab present, stem fixed, no slab, and stem fixed, slab present. And we'll take a look at how each of these affects our overturning moment calculation. When you have no slab present, the shear from the stem, along with the earth pressure acting on the footing and key depth, are going to contribute to overturning. If our stem is pinned, the pin connection is going to produce no moment at the base, so the only contribution to overturning here is going to be from the lateral forces. When the stem is pinned and a slab is present, the pin connection produces no moment at the stem base, and the slab is going to absorb all of the lateral forces. So we have nothing left to overturn the footing, and our overturning moment is going to be 0. For stem fixed no slab, here we have no slab again, so the stem shear and earth pressure on the footing and key depth are going to still contribute to our overturning. And then because we have a fixed stem, we now also pick up a fixed end moment for this overturning moment calculation. And then for stem fixed slab present, the slab is going to pick up the lateral forces, but the slab is not going to resist the fixed end moment, so the overturning moment is going to come from the fixed end moment alone. And then another thing that I'd like to mention here is a recent change to the restrained retaining wall module that some of you might have noticed regarding the stem fixed condition. In previous versions, fixed end moments at the base of the stem were excluded from the footing eccentricity calculations, and this resulted in a uniform bearing pressure distribution. After some internal review and some customer feedback, we've updated the methodology, and it has been revised to include the moment in the footing equilibrium calculations, and we now transfer the moment to the supporting soil. If you'd like more detail on the calculation of soil pressures in the restrained retaining wall, we have a comprehensive FAQ on the topic, and it includes this great graphic that Derek, one of the engineers on our team, put together to just help kind of visualize the effects of these different loads across the 4 permutations. So if there's any confusion about soil bearing pressures, I highly encourage you to check this out. Back to our results view, in the stability tab, we can review the reaction force at the top restraint, which is provided so the engineer can confirm that the support is adequate to restrain the slab. We can also review the resisting moment calculation. The resisting moment is going to be the sum of all clockwise or stabilizing moments about the toe. These are going to be produced by the vertical loads, and these loads are going to include the soil weight, surcharge loads, if you've selected to include them, the self weight of the stem and footing, axial loads, and then any adjacent footing loads. And the final two tabs on the output side of the screen are the construction and wall loading tabs. And these can be reviewed to confirm that you are satisfied with your final design. So now that we've gone through that example, it's time to open it up for Q&A from the audience.
All right. We have a lot of great questions, and let's go ahead and get into it. First question is actually regarding cantilever retaining walls. So I'm definitely going to encourage you guys to go and check out our previous office hours regarding cantilever retaining walls. But the question is, on cantilever retaining wall designed on pier footings, shouldn't there be a grade beam designed to get the loads to the piers? So there's a few confining assumptions when you toggle over to cantilever retaining wall footing on a pier. And if I'm not mistaken, Chelsea, feel free to chime in on this. If I'm not mistaken, that basically assumes that you have essentially a cantilever pier, a laterally loaded cantilever pier foundation directly centered under the wall. And so it's, if I recall properly, that workflow is constructed so that the bending moment at the base of the cantilever retaining wall is essentially transferred directly to the pier foundation. Chelsea, go ahead if you have thoughts on that.
My understanding is in line with yours. If anybody has concerns about a particular design, I would say that the best way for us to address that would be to send us the project file and kind of let us know what you're seeing on your end. If you have any hand calcs or specific concerns about a condition, we'd be happy to take a look at that and let you know what we're seeing on our end.
All right, next question. Regarding the brief mention of load linking, after you select recalculate your linked loads, is there a way to see which designs are now failing without having to select each one individually and review the design summary? So the core behavior of the project manager view has not fundamentally changed right now. And so as you guys know, historically there's never been any kind of a mechanism to see at a glance overviews in the project manager as to whether each individual calculation is passing or failing. So that behavior remains unchanged right now. The best way to see if a calculation is passing or failing would be to regenerate your reports and then review the preview for each report by just clicking down. You don't have to all the way open each one, but you should be able to single click each one and see the report preview, which will give you design status information. The reason that the project manager doesn't have that capability right now is primarily just because not every calculation that ENERCALC supports actually boils down to a simplistic yay or nay, pass or fail. But feel free to explore that capability and then follow up if you have more questions. And I do see at least one person has raised a hand. Just so that you guys know, we do have the Q&A dialogue for you guys to submit questions. We don't do questions verbally just because the logistics are more difficult in this format. All right, next question. Is it possible to get a copy of the slides for this class? So like we mentioned at the start of the session, every session recording does get placed on our YouTube channel, which you can access either directly on YouTube or through the enercalc.com office hours page. Chelsea, correct me if I'm wrong, but I don't think we're in the habit of publishing or sharing the slide decks, correct?
That is correct. We do not publish the slide decks, but we do have the recordings available for rewatch.
Perfect.
If there's a certain visual that you find helpful, if there's, a specific thing that you wanted, feel free to reach out to support@enercalc.com. We don't have a plan to publish the full slide deck, but if there was a particular thing that you found helpful or you wanted to reference, we can get that over to you.
For sure. Or feel free to ask now if you want to drop another question and just say, hey, can we go back to whatever slide, absolutely feel free to chime in with that, and Chelsea can revisit something that was in today's content. All right, next question. In the program, when you put a surcharge, does it assume it is dead load or live load for the reinforcement requirements? So this is an interesting question, and it's an important thing to be aware of. In the case of how the ENERCALC module is handling it, the only thing that surcharge load does is actually increase horizontal pressure, lateral pressure on the wall, which ultimately is going to be your soil load H, hydrostatic pressure. And so rather than being treated like a dead load or live load with respect to those LRFD load combinations for reinforced concrete design, the surcharge loads are simply acting to increase the horizontal hydrostatic pressure. And so ultimately it's behaving like earth load, if that makes sense. Feel free to ask any follow-ups. And Chelsea, go ahead if you have thoughts to chime in on any of these.
Yeah, this does differ a little bit between the modules. In the cantilevered module, surcharges are considered additional load from additional like soil weight. So the calculation just does a kind of a transformation into additional soil height. And then for your, I believe for your axial loads, those are considered live loads. If you have a
Yeah, I
question about a
believe.
particular calculation, I would recommend sending that to support. The the way that it's treated across the modules is not the same for
Yeah,
one
and for
reason or
sure it would
another.
vary. It would vary from cases where you're allowed to explicitly put loads directly on the wall. Obviously, in that case, it makes sense to explicitly categorize those. Whereas if it's just a surcharge, which is increasing hydrostatic action on the wall, is a little bit of a different case. All right. Next question. Is the module automatically modifying the point load based on the height, or does that need to be considered prior to entering the load? So, good question from Mike. I was looking at this question earlier, and I'm not 100% clear on specifically which point load you're referring to in that question. If you wouldn't mind following up with a little clarification, but Chelsea, go ahead if you have thoughts off the top of your head on Mike's question there.
Can you repeat that question for me?
Yeah. Is the module automatically modifying the point load based on height, or does that need to be
Oh,
considered prior to entering the load? I'm not
yes.
clear if this is axial load on the wall or surcharge load offset from the wall.
Okay. If it is axial load, I'll bring up this image. If it is axial load, the module is not going to reduce the load, or consider how the load spreads out over the height of the wall. So that's something that you would have to reduce before you enter that load. Um, if you have any additional info about that question, let us know and we can take a look.
There, he dropped in axial load, so that should answer
Okay.
the question.
Yeah, so the
Perfect.
axial load is not going to be reduced along the wall height. That would be something that you would do manually. And again, considering, I'll pull up this image as well. The restrained retaining wall is going to look at three different sections along the height of the stem for design. So it's going to be at the base of the stem, at the point of maximum moment, and then at the top of the stem. So if one of those sections governs, you might need to run a couple of different calculations with that load that varies depending on where it is along the wall height.
Perfect. Okay, next question. At the end of the presentation, could you explain the difference in how ENERCALC calculates the soil pressure based on whether the stem is fixed or not fixed to the footing? This is a great question. We actually have some relatively recent new documentation about this on our help, which you can find either with your install or online in our web-based help under calculation modules, earth retention, restrained retaining wall, calculation of soil pressures. I'll go ahead and drop a link in the chat for that. But Chelsea, go ahead if you want to dig into that a little bit. I know you touched on it near the end of the session.
Yeah, so when a stem base is fixed, you are going to have a moment due to the stem that is occurring at the base of that wall. And that moment is going to contribute to your overturning moment, regardless of if there is a slab present or not. So we can see, I'll pull up my pointer. Here, stem base is fixed. We see moment due to stem. Fixed end moment is going to be included in both our slab present and our slab not present conditions. And then this overturning moment is what we're going to use to then determine our eccentricity and then our soil bearing pressure calculation. And like Seth said, we do have that FAQ doc. It kind of breaks down the different steps in the soil bearing pressure calculation. So if there's still a little bit of confusion, definitely encourage you to check that out. If you have any follow-up questions, feel free to drop them here, or you can reach out to ENERCALC support and we can get those addressed for you.
All right, let's keep moving here. Next question. Trying to make sure we go through these in order. For concrete restrained retaining wall, if the width is more than 12 inches, generally we'll use 2 layers of vertical bars. Any section can show it, or if we need 2 layers of vertical, for example, 6 at 16, or should I input number 6 at 32? So I'm not 100% sure on what's being asked here, but it sounds like it's sort of a two-part question. Number one, does the restrained retaining wall module consider or analyze a doubly reinforced wall behavior? And number two, is that shown schematically? So Chelsea, go ahead if you want to jump in on that. But it's as far as I'm aware, obviously you want to keep in mind the diagrams that you see are predominantly schematic. They're not always going to be perfectly feature complete reflection of what's specified in your calculation. They're not drafting level schematics. But go ahead, Chelsea.
Yeah, so I pulled up this construction view just so we can kind of see. This is a schematic view. It's intended to show you that when you specify edge reinforcement, the reinforcement is going to be placed on the tension face of the wall. The retaining wall modules do not consider the contribution from the reinforcement that's placed on the compression side. So all of the wall calculations are going to be done assuming a single layer of reinforcement placed on the tension side.
Perfect. All right, next question. When designing a basement retaining wall, many contractors want to be able to backfill the wall before the floor diaphragm is installed. So the wall needs to be designed as cantilevered and not restrained. Is there any thought in the future to be able to carry over the cantilever design into the restrained module so the wall footing rebar design doesn't need to be entered for each module? So that is a great feature request, and we'll make sure that we go ahead and log that and pass it through to the engineering team. Don't have that feature at this time, but we do appreciate you kind of diving in with that. Because that's really good insight about the workflow. So appreciate that, Jason.
Yeah, that's a good feature request. And that also is a good thing to point out is that when you do end up doing your design in the restrained retaining wall module, it is going to assume that the restraint is present and is ready to
Yep.
take that force. So if you have a construction condition that you need to consider, then doing that calculation in the cantilevered wall first would be appropriate. Sometimes you can have like a reduced factor of safety because the construction loading, and then you can do both designs and see which one governs. But we'll definitely keep that feature request in mind. Thanks for that.
All right, next question. For a restrained retaining wall, are we presuming the builders will shore the wall during backfill and prior to the slab being poured and set? That's actually pretty closely related to the previous question that we just addressed. Essentially, there's no sequencing or construction staging behavior explicitly built into the module. So if there's, like we just discussed, if there's sequencing issues that have to be considered, that at this time might involve alternatively checking a cantilever configuration for the wall, or as the engineer specifying that you do need some kind of shoring if you're going to backfill before the diaphragm is in place. Right now, the module doesn't handle those kind of sequencing issues automatically. All right, next question. Does ENERCALC have any module to design in-ground cast-in-place concrete vault or box culvert subject to traffic loads? So not at this time. For those of you who've used ENERCALC for a while and are familiar with it, you know that we currently only support building structure design standards at this time. So even though you do have the flexibility to create your own load combinations, you could imitate some AASHTO-like analysis if you had the need to do that, but you're not going to be able to apply, for example, AASHTO concrete capacity checks and so on. ENERCALC is focused on building design standards at this time. So ACI for concrete and no traffic load handling at this time. Now, that with that being said, you can use ENERCALC 3D to analyze moving loads. You can also do plates and shells and membrane type structures that are modeled in 3D in ENERCALC 3D. And so if ENERCALC is your tool of choice and you have occasional one-off projects of that nature, you do have some capability to roll your own smoke with a 3D finite element model, do moving loads on it, so on. ENERCALC 3D is pretty feature rich in that regard, but there's nothing out of the box as a module as such that would allow you to do vaults or box structures, if that makes sense, especially where traffic loads are involved. Great question, though. All right, let's keep moving down the list here. Anything you can do to provide flexibility in loading, not having to create different calcs for wind or seismic can be helpful. It gets tedious when having two separate calculations to have to revise wall construction based on separate design calculations. And I'm obviously on these that are feature request oriented, we pass these. The engineering team is the ones running this session, so the engineering team will be available of your feature requests, and we always appreciate those feedbacks. So
Yeah.
we always check to see if there's existing feature requests, and if there is, then that goes on the pile with the existing request to help move the needle on that priority, or we create new feature requests as we go.
Yeah, for that specific request, to allow users to apply multiple load combinations, similar to kind of the behavior of the other ENERCALC modules, that is an existing request that we're tracking. So we can go ahead and associate your email with that feature request so you can be notified if there's any progress.
Perfect. All right. When designing foundations in ENERCALC, what is the recommended method for considering frost heave? Should it be modeled as an uplift load, lateral soil pressure, or another load type? Also, where in ENERCALC should this load be entered? So this is definitely pretty far on the side of engineering judgment. There's no native out-of-box functionality in ENERCALC modules at this time to consider effects like frost heave. So for now, that's going to have to live more on the engineering judgment side. This one is phrased as if it's referring to foundations rather than retaining walls. On your foundation modules, you do have a variety of capabilities for applying loads, but we don't have a specific recommendation for how to consider frost heave, though you do have the ability to specify uniform overburden loads that extend all across the footprint of a footing. So you do have capability to customize how the footing is being loaded for sure. All right, next question. Does the module change the direction of seismic and wind forces for designing the footing, checking soil pressures, and stem designs such as plus or minus wind, plus or minus seismic?
The module does not currently automatically switch the direction. So if you need to consider multiple directions, then the recommendation at this time would be to copy that calculation and reverse the directions manually. That kind of ties into the load combination feature request that had been mentioned earlier.
All right, next question. Is an 8-inch wall with bars centered really fixed? Again, that's going to be a secondary judgment decision for the engineer to make. The ENERCALC module itself, I don't think, and Chelsea, jump in and correct me if I'm wrong, I don't think that the module itself gets heavily into detailing as far as um, actual detail bars or continuity bars that pass from the wall into the footing, correct?
Yeah,
So,
really good point. For the examples today, we did assume a fixed stem with bar centered. So um not a really a recommended detailing, but it ultimately is up to the engineer to decide if they feel that the condition they've detailed is going to be a fixed condition. I think I mentioned that there's no like intermediate fixity that you can define. So you do have to select either pinned or fixed. And that's just up to your judgment and your detailing to determine if that is an appropriate assumption.
all right, next question. Where do we find the FAQ doc? And the answer is right here. I will drop it in the chat for you. But for those who are not familiar with the FAQ doc or don't know how to access it, you can always head over to enercalc.com under the For Our Users drop down menu. We have a lot of handy links for documentation, and the FAQs are easily found right there within the documentation alongside the user manual. Good question.
Yeah, I can actually show that real quick if we
Yeah, for sure.
So I'm on enercalc.com right here. Seth had mentioned we're going to pop over to our For Our Users dropdown. We're going to select documentation. And then this top option is going to be the user manual. This will be the web version of the user manual. And then down here at the bottom, we have our FAQ. So this is where you can come to find a list of frequently asked questions for our different modules.
Oh, there you go, Chelsea. You have another vote for that feature request for load reversal or wind and seismic reversal.
Awesome. Yeah, if you sign up for the session using your email, then we will take your email and add that to the feature request. Getting feedback from multiple users is very helpful. The more we see demand for something, then the higher it goes up on the priority list. Project Load Group Builder is an example of that. That was something that was pretty hotly requested. Load linking as well. That was something that a lot of users would have requested. So if you want to see something, please reach out. This is a good channel to do it, or emailing support@enercalc.com. If we already have an existing feature request, we'll add your vote to that. And if we've not received that request before, we'll create a new one and then track that going forward.
All right. And then our last question here, Chelsea. Do I have the ability to see shear and moment diagram? And I believe the answer is not at this time. There are a couple of earth retention modules where we do show a moment profile, but not in the cantilever or restrained retaining walls at this time. We do show the construction schematic and the wall loading. The wall loading shows you soil bearing, the resistance at the toe, the horizontal resistance, pressure at the toe, and the retained side pressure profile, as well as any external loads like surcharge or wind and seismic. There's not a view at this time that actually shows a shear and moment diagram. In the case of most of our earth retention modules, or at least today's retention module, the restrained retaining wall, those moments and shears that are being presented in the results output are being computed directly through simple equilibrium, not through finite element analysis that would result in a complete shear and moment profile. Now, that's not true of all of our modules, but in this particular case, that's what's being done. Good question.
Yeah, and I'll also comment here. If you are curious to kind of go in and compare how things are being done, one thing I did was I used the general beam analysis module to apply the lateral loading on the stem and then either select pin pinned or pin fixed condition so that I could, get those reactions and kind of compare those to the outputs from this module. So if you're digging into one of your calculations, the general beam analysis module could be a helpful tool for you.
All right, we have another question. Has ENERCALC ever considered nearby buttresses, 90-degree wall turns, etc., to include the contribution of horizontal bar and wall design? Um, we'll go ahead and process that as a feature request as well. We don't have anything actively in development to do that right now, but for sure, buttressed walls and horizontal stiffeners are um, a valid design option that engineers have to turn to sometimes. So,
Yeah, that we
yeah, that's a
actually
great
we
thing to be aware of.
are tracking that feature request. That feature
Okay,
request first came in, I think, 2 days ago. So we can
cool.
add your email to that request.
Fantastic.
All righty. Are we wrapped up on Q&A?
I think that was the last of it. That was a great set of discussion there. So thank you guys for chiming in on all the questions. Um, Chelsea, you want to go ahead and wrap us up with a teaser for next month? What's on the agenda?
Of course I do. So next month's session is going to be on August 12th. It'll be the composite steel beam module. We'll be revisiting that module to see what has been updated since the last time we did a session on it.
Mac's favorite module.
Yeah, Mac is returning to office hours. Uh he will be our presenter for this session, which should come as no surprise to anybody who knows Mac's absolute love for this module.
That's
Um,
right.
Genuine. He really does love it. So yeah. Thanks everybody for being here. I appreciate you taking some time out of your day to sit with us, and we appreciate all of your questions. We hope to see you at next month's session, and I hope that you guys have a nice week and you're staying cool wherever you're at.
All right, fantastic. Well, once again, we thank you guys all for your time. We appreciate everyone being here. We look forward to these every month, and we will look forward to seeing you guys next month. Thank you all very much and have a good one.